So before we push on with the course, like we start every course with why. You know, why do we need to study now? Because you know, I can hold a map, look out the window, work out where we are. Why do we going to spend like 15 hours and this entire great big thick green book studying Nav? Rob, what do you think?
Sorry, Mike Faff. So obviously, so that we can safely navigate our place from A to B, adhering to all the rules and regs of the air.
Yeah, I think you've got it in one. There is that the key word there is safely, and by safely, what we mean by that is you're not going to penetrate airways, restricted airspace, fly over things you shouldn't be. You'll have worked out all of the things in advance, what you're going to be covering, things like diversions, things. What do you think is the number one cause of aircraft incidents? The number one cause of aircraft fatalities is bad weather in flying into IMC. But what do you think is the biggest cause of aircraft incidents in light aviation? Well, they're actually fuel related issues. And fuel related issues is all comes down to one thing. How much have we got? How long is it going to take? And how much are we going to use? And that's all down to navigation. So, so we've got the safety aspects. We've also got the other thing is that you've probably heard your instructor say the three things you do in a plane in this order is aviate, navigate, communicate. And half the battle is with flying is that flying a light aircraft is actually once you get beyond a certain point, it's actually remarkably easy. It's just like driving a car, and you'll find that you'll jump in a plane, you'll do it naturally, and off you go. It doesn't really take a lot of thought, even though you've got lots of knobs and switches and things. You know, just like a car, this hand will be reaching over, doing things, working things, clicking things. Yeah, your brain won't know what this hand is actually doing. It will just be like clicking buttons and switches and things. And even on big complicated aircraft, you know, it will just be working things, and your brain won't be in control of this hand. It will just be moving knobs and switches and things, and you'll kind of do that automatically. But the real thing you've got to be able to suss out is this whole management thing. It's not so much the skill of flying the plane, it's the management of the plane. In other words, what I mean by that is that we've got to aviate, navigate, and communicate. But the only trouble is the human brain, as soon as you get a slight problem or anything that's not quite right, you haven't got enough spare brain capacity to aviate, navigate, and communicate all at the same time and do them all in that sequence. Because when aviation starts to go wrong, your navigation starts to go wrong. That causes more aviation problems, and then you can't communicate your problems, and so you're into this spiral of despair, you know, where things are going up the creek. And by having a very organized plan of how you're going to get from A to B means that the navigate part of aviate, navigate, communicate is very much managed. and you've already got pre-planned everything you need to know to navigate that aircraft, giving you more time to aviate and communicate. And the more and more time you can get, the more easier you'll find that as a pilot, when things go wrong, you can easily sort those issues out. And of course, the other big reason why we have to have everything planned in a plane is planes don't stand still. You know, I teach navigation on boats and things, and yeah, you know, you can stop a boat, you can park a car, you can work out what's going wrong. I'm sure many of you have just like been driving along through an unknown town, and you know, yeah, you just haven't a clue where you're meant to be going, and it's all, and in the end, you just have to park the car at the side of the road, you know, and you spend 2 minutes kind of getting your arse in gear, right? Okay, right, where do I need to go at this roundabout, you know? And you know, planes don't stand still, you know, they're flying all the time. So you know, you've got to be able to have this plog of exactly how you're going to get from A to B. And everything that we cover on this course is culminating in how to write a plog. So the navigation course is divided into 2 exams, really. The navigation exam and flight planning and performance. There's not huge amounts of the 2 subjects are replicated. So when I'm going to cover nav, I'll also be covering a big chunk of the flight planning and performance syllabus in this course. So you'll already be more than half the way through flight planning and performance when we've completed nav. And you know, sometimes we mix the 2 courses so that you can cover yeah, you can do the flight planning performance exam at the same time as nav if you want to. Sometimes, you know, people prefer to if they've got a lot of other workload, they might want to maybe delay flight planning performance for another month or whatever. So that's entirely up to you. So let's push on with nav. If there's no questions on what we're going to be covering and the syllabus and things like that, we'll push on with the course. So all nav courses start with one of these. So let's just recap the basics of our O-level geography. Rob, what's a day? Tell me what a day actually is. What does it actually mean physically?
So in 24 hours, the Earth will do 1 full rotation.
Yeah, so the Earth is in constant rotation, isn't it? And it takes 24 hours to do 1 complete rotation. So, Rob, at what point does the Earth rotate through?
Through its axes, north and south, which is actually on a tilt of about 23 degrees.
Yeah.
If I remember.
That's right. And it rotates around true north and true south, doesn't it?
Yeah.
Yeah. So, Claire, what's the difference between true north and magnetic north?
True north is, I don't know how to explain it. I don't know how to explain it, sorry.
Go on,
True
Will,
north is like at the top of the axis, isn't it?
yeah, true north is the point which the Earth rotates around, yeah? As Rob just stated. Magnetic north is the point where all the compasses point to, and they're not quite in the same place, are they? All the compasses point to magnetic north, which changes a tiny bit all the time. Magnetic north always moves slowly round the North Pole, round about this point here. It just keeps rotating round and round, and every year it moves a tiny bit more, and then eventually it'll get back to where it started. But of course, true north never changes. The Earth always rotates around the same point. When we are talking about a day, what actually then, Claire, is a year?
A full journey around the sun.
Yes, so as the Earth is spinning and takes a day to rotate, it also moves around the sun, and it takes a year to go all the way round the sun, doesn't it? Just a little bit more than 365 days. And for the purpose of navigation, we've divided the Earth up into lines. These are imaginary lines that we've drawn on the planet Earth. These are the latitude and longitude. But we've also got a couple of interesting extra ones, which is the Tropic of Capricorn, Cancer, the Arctic Circle. So let's just explain those. Is that as the Earth is moving around the sun, and as Rob's quite accurately pointed out, the Earth is tilted. Well, of course, as it moves around the sun, the tilt of the Earth is going to change relative to the sun, which means at some points in the year, the Earth is rotating like this, facing the sun, and at other points of the year is rotating. It's rotating like this, pointing at the sun. So in other words, the sun at one point in the year will be overhead here. Another point of the year, it's going to be overhead here, and the Earth will be rotating like this because of the tilt of the Earth. Now, these two extremities, where the sun is directly overhead, these are the Tropic of Capricorn and the Tropic of Cancer. So the Tropic of Cancer is the northern point, and the Tropic of Capricorn is the southern point. So they are physical things. They are imaginary lines, but they're physical. In other words, human beings didn't invent them. They are a function of the Earth. And then we've also got the Arctic Circle and the Antarctic Circle. So who knows what the Arctic Circle is? Well, the Arctic Circle.
Pole.
Yeah.
Oh, sorry.
Go on.
I was just going to say the polar ice cap at the top. So
yeah.
the Arctic is the top, Antarctic's the south.
Yeah. But when we're talking about the Arctic Circle, these are physical things as well. What do we actually mean? Well, I'll explain. What they actually are is that they are the extremity of the Earth where the sun doesn't set for a period of time. In other words, the bottom edge of the Arctic Circle that heads off, where are we? So the bottom edge of the Arctic Circle kind of heads off round here. This is the point where there's one day of the or one night of the year, the it never actually, the sun doesn't rise, and one night where the sun never sets. In other words, they're pointing so much at the sun that even when they're right over here at night, the sun is still shining. And likewise, at one point when they're pointing in the other direction, where there's one day where the sun never rises. In other words, it's dark all the way during the day, and that's what we call the Arctic Circle. And of course, there's another one at the Antarctic Circle. And of course, the more nearer you go to the North Pole, the true north, the more pronounced the night and day is. So right at the very North Pole, you'll get night for a much longer period and obviously it will be sunny during the night for a much longer period as well. So in order to navigate, the Earth is divided into lines of latitude and longitude, and these are based on the rotation points of the Earth, the true north, because this point is known and this point is known. These can be identified using various instruments and star movements and things like that. You can actually work out exactly where true north and true south actually is, and you can actually use instruments like gyros and things, and you can walk to the North Pole and you can bash a stick in the ground and say, right, I've established this is true north. This way, of course, you can't actually draw lines this way because there's no point of reference. You know, the Earth is just a sphere. So what the early navigators did is they actually said, well, obviously London is the center of the universe. So what we'll do is we'll make 0 degrees longitude go through the Greenwich Observatory. And in fact, if there was a lot of logic for that, because at the time the Greenwich Observatory was the most accurate observatory in the world, and it had some very precision made equipment where you could measure angles of stars extremely accurately. And so they actually said, well, look, this is where the telescope rotates, the axis it rotates around. So what we'll do is we'll just paint a line on the ground and going right through the axis of the telescope, and we'll call that 0 degrees. And from here on in, everything's going to be measured relative to that. And because we know it passes through the axis of the telescope, we can measure all the star angles and things, and we can actually start thinking about making things very accurately. And that's really how the Greenwich Meridian came about. And in fact, the Greenwich Meridian is still there. I mean, if you go to the Greenwich Observatory, there still is the piece of brass, a brass strip on the ground with painted white, which actually says that that's 0 degrees. So I've got a nice little video of that. Okay. A nice little video of this that's not it's not very loud, is it? Ah, shit. Right, let me a short, a tiny interlude while I find out why that's not actually no, it's not working, is it? No, that's not what I want. Ah, right, that's it. Right. God damn it. Um, okay, right. Okay, I'll abandon that. Right, I don't know why that's not working. There's it sounds not working. That's because I'm doing something slightly different on this session. Is that I'm not using an intermediate source. I'm doing everything straight off my laptop. But doesn't matter. Right. So let's talk about latitude and longitude. Well, I normally like to do this off a video because it's not the world's easiest thing to draw a circle. More like a potato, but hey. So we know that we've got the North Pole and the South Pole, and we know that these are fixed. This is true north and true south. So we could draw a line between them that would go straight through the middle of the Earth. And then we measure latitude by taking a right angle from between north and south, and we call this the equator. And then what we do is we put a series of lines on the Earth. These are lines of latitude, and the angle it is relative to the equator is we imagine that there's a line that's going round the Earth. And so if this is, say, what's that, about 15 degrees, then 15 degrees north would be, if you like, a sort of circle that would go all the way around the Earth and then round the other side. So that would give us a point north or south on this globe, would give us any line. And because it's relative to the rotation of the Earth through a north and south, you can imagine that by having the right sort of technology and the right equipment, we could actually work out where we are north and south. So we would say this is 15 degrees north, and there'd also be a corresponding here, for example, this would be 45 degrees. This would be 45 degrees south. So there'd be one here. And you could probably imagine that, they don't have to be, we could have another one here that would be 33.6 degrees. So they don't have to be exact, so multiples of degrees. They can be, precision as precision as we like. And then what we do is we take Greenwich meridian, and then we draw another series of lines going all the way around the Earth, and we make sure that the 0 line, call this one 0, passes straight through the Greenwich. And then once again we measure relative to this line. We then measure east and west, and then we can draw other lines on it. And these are the lines of longitude. And once again, starting at the Greenwich meridian, they can go all the way around the Earth to 180 degrees the other side, or they can go 0 to 180 degrees and go the other way. And we call them east or west. So this is north and south. We've got lines that extend east of Greenwich, like this one here is 10 degrees east, and then we've got ones here, and this would be, say, 30 degrees west. So by using lines of longitude and latitude, we can actually describe anywhere on the Earth. So the lines of longitude are going this way, like this, and lines of latitude are going up and down. So, Will, lines of latitude, what do they go from and to in terms of number? They start at 0, which is the equator.
It would be 180 or 90.
What do you reckon? Well, it's actually 90, because the most a line of latitude can be is it's 90 degrees to get to the North Pole, isn't it? Yeah. And it's 90 degrees south to get to the South Pole. So a line of 45 degrees north would be about here and would go round the Earth like this. And 45 south would be round here. So would you say then, Will, that all lines of latitude are the same length?
No.
No. So which is the longest line of latitude?
Around the equator.
Yeah. And how long, if you traversed all the way around the Earth along a line of latitude, how long is 90 degrees north?
I'm not sure.
Well, it's the point which is at the North Pole, isn't it? So that line is going to be, it's not going to have any length at all.
Okay.
In other words, if you're at 89.9 degrees latitude, you're just a tiny weeny bit away from the North Pole. So it's describing a circle that you can probably walk around, isn't it? Because it will be a very, very small circle. So, Rob, lines of longitude, they start at where?
So they start on the 0 running through Greenwich.
Yeah, and are they as I go east and west? Do they get smaller, shorter, or are they the same length?
They'll be the same.
Yes. So in other words, all lines of longitude then are the same length, aren't they? All these arcs, whereas lines of latitude get smaller as we get north. So Claire, lines. We've talked about lines of the latitude goes from 0 to 90. So it's 0 to 90 north, 0 to 90 south. So lines of longitude that start at the Greenwich meridian, that's 0. What do they go from and to? Obviously, they start at 0. What do they go to? What's their range?
Between the poles?
Well, I think lines of
Oh.
longitude go this way, don't they? They go from every line of longitude goes from the North Pole to the South Pole, yeah? As like segments on an orange. So what's their range? If they start at naught, meaning it goes through the Greenwich meridian, what do they go from and to?
Not to 360.
That's pretty good. It's not quite 0 to 360 because what happens is we measure them west and east. So that means they go from 0 to 180 degrees east and 0 to 180 degrees west. So in other words, that if we go round the Earth to here, this point here, this is the opposite to north. So this is 180 degrees east and west, runs down the Earth this way. And unfortunately does a little wiggle through the little island where it does a tiny little excursion. So lines of latitude go naught to 90 north and south, and lines of longitude go 0 to 180 degrees east and west. So that means that lines of longitude have got more digits in them. There's 3 digits you need to represent a line of longitude, and there's 2 digits you need to represent a degree of latitude. And one of them is north-south, and the other one is east and west. And this is one of the few points in aviation where we don't use the terms November, Sierra, Echo, and Whiskey. We actually use the actual words north, south, east, and west. Luckily, they're all nice and short words and fit into phonetic vocabulary quite well. So we've got a way of representing any point on the Earth using lines of latitude and longitude. But the next problem which we've got is, how do we then draw a map? Well, the early sailors could obviously have a great big globe on board the ship. And as they charted the seas, they could actually draw all of these places on their globe, and they could measure exactly where they were. They could measure their kind of latitude and longitude through various observations of the stars and things, and there's quite a lot of mathematics involved and you can actually work out by looking at stars, measuring angles in the sky, work out where you are using sextants and all sorts of clever tricks, and measuring the time it takes from one star to move to one point to another point relative to another known movement of the sky, for example. You can actually kind of work out where you are. And you can draw these things on the Earth and draw all the continents, and that's what they basically did. All the explorers went all the way around the Earth, drawing their maps onto their globes. It's curious, isn't it, when you look at a globe, just how big Australia is. And it's quite incredible that all the early explorers took years to find Australia, and they kind of followed this chain of islands here and followed here and all around here, and they discovered all of these islands before they discovered Australia. And in fact, Cook discovered Australia by going the other direction. He didn't bump into it this way. He was heading back to the UK and discovered this little island called Australia. And you think, how on earth could they have missed bloody Australia? It's fucking occupied so much of the earth. But hey, you know. So you can get these globes, and obviously then they had a master globe back at Greenwich where they would then keep it updating. But this wasn't really a lot of good because, yeah, how do you set out in a ship with a globe? You know, you want another means, don't you? You want to be able to convey that information into a flat form. You know, you want to take with you on a boat, you know, something like this, a sheet of paper, you know, that somebody can make, that's got all these that you can zoom in on, that's got the names of the towns and things, and maybe a bit more detail on it. You know, you can't draw all that information you want on a globe. So they had to produce bits of paper, which are called, and these are called charts. But how do you convert a globe into a sheet of paper? You know, how do you convert something spherical like this into something that's flat? Because this isn't going to fit on that. Well, that was a big problem. So they came up with several ways of doing it. So the first method is, this is a globe you can see that has a light in it. So what the early people used to do is that you could get a sheet of paper, a bit of photographic paper, and you could like have a light in the middle of the globe, and you could put the sheet of paper round the globe like this, and then you could project that light onto the sheet of paper and expose it, and that would produce you a simple chart. And we call that a Mercator projection, named after the guy that thought it up. But you could probably see immediately there's a problem with Mercator projections, in that if you imagine you've got your sheet of paper here, and what you do is you've got your light bulb here, and this is shining through onto the piece of paper. If I draw these roughly equal distances, can you see what's going wrong? Is that what's happening is that if I can probably draw this a bit more accurately actually. If I draw this in the middle here, there we go, it's a bit more realistic, isn't it? You can probably see that the distance between there and the distance between there and there aren't the same. In other words, as you get further up the map, the distances vertically are growing. So as we get further away from the equator here, is that the lines are growing. So in other words, if we had a map with equal lines of latitude on them, so if we had a map showing the equator, and then we had 10 degrees, 20 degrees, 30 degrees, 40, 45, 50, 55. Yep. So in other words, if we had all these lines of latitude on the map, our map would look like this. We would have our equator running through the middle. This would be naught. And then we'd have 10 would be here. But the trouble is that 20 would be here, and 30 would be there, and 40 would be here. So what's actually happened is you can see that although we've gone for an equal amount, 10, 20, 30, 40, the distance between there and there, there to there, there to there, and there to there is getting more. So in other words, that although we've converted the globe to a map, the map isn't a true representation. It's distorted everything in the plane of projection. So if you were to travel from any 2 points here, we could measure the distance, say, from there to there, and we've travelled through 10 degrees of latitude. But if we measure the distance from there to there, you can see that in reality that distance and that distance is the same, but on the map they are completely and utterly different. In other words, the distances aren't being maintained on the piece of paper. And in fact, if you think about it, I mean, this must be the case, because you can't take something that's spherical and sort of lay it out flat and then try and make that to be an accurate representation, because if you take something that's spherical and you make it flat, it's always going to be distorted in one way or another. Yeah, that's just fact of life. So not only the distances going to be incorrect, but you can probably get your head around the fact, and you can probably also see that that if I sailed a straight line on the globe, because it's distorted as we go up. If I was just sailing a straight line, a perfectly straight line on the globe at an angle here, well, what's going to happen on the map is that our line would get distorted like this. So in other words, what we would see on the map isn't actually a straight line at all. And in fact, if we drew a line, a straight line on this map, like this, and we sailed this straight line, in fact, we would actually say, in reality, sail an arc on the globe, which obviously wouldn't be a very good thing to do. So in order to try to compensate that, they developed other methods. And one of the methods was to take, instead of just wrapping the paper around the globe, what they did was they formed it into a cone, and like this, and then they put the globe in the middle of the cone, and once again lit it up and projected it onto the cone, and this gave a much better representation. And we call this a Lambert conformal conic projection. But you can probably see that it's still got problems in that you know we can't hide the fact that you can't take something that's a sphere and roll it out and make it into a beautiful flat. It just isn't possible. But by making it into a cone, we get a slightly better a representation. Now, why do we want to use sort of what's called a conical projection as opposed to say a Mercator projection? Well, the thing about conical projections is that they generally preserve distances better. So if you draw lines and measure things on a conical projection, it generally works better. But the biggest disadvantage of a conical projection is that as soon as you try to do it for a much larger area of the globe, in other words, as soon as you try to do it for like, you know, hundreds and hundreds of miles, it all goes, it distorts it massively. You get massive curved lines. In other words, that on a Mercator projection, that generally our lines of latitude and longitude are straight. They're at right angles, but they're just massively distorted. Whereas on a the same thing as a conical projection, what you tend to find is that the lines of longitude tend to diverge out like this. In other words, the lines of latitude and longitude don't cross at right angles on your chart, but the distances and lines you draw on it's a much better representation than a Mercator projection. So you do tend to find that most aviation charts are Lambert's conformal. And there's exam differences on exam questions on what's the difference, you know, what are lines preserved, latitude and longitude, how are they represented, what measures distances best, blah, and all that sort of things, bits and pieces. So I've got a nice at least the Poolies doesn't need it, at least the PowerPoint doesn't need any sound. So it's gone to number 7. So this is showing you a typical how you make a Lambert's conformal. So in other words, you've got the globe with the bulb in the middle of it, and then you've tried to wrap the bit of paper around it, and then you spread the bit of paper out, and this is basically what it would look like when you make the chart. So you can see how it's the latitude and longitude have been distorted. In other words, the further you get away, the more the lines of latitude are going to be circular, and the lines of longitude all tend to diverge into a point. But if we take the Mercator projection, once again, we wrap the bit of paper around the globe, but the difference is that the actual vertical lines of a Mercator projection are all vertical. So in other words, that the lines of latitude and longitude cross at right angles, but of course it distorts. In other words, the gap between them it isn't a very accurate representation. Now, the difference between the line we draw on a chart and the line we draw on a globe, we call them rhumb lines and great circles. So what actually is the difference? Well, the rhumb line is a line you draw on this, is a straight line you draw on a chart. So in other words, if we take a map, we'll draw a line on it. There we go, Limassol pathos, draw a line on it, doink. But that's actually what we call the rhumb line. It's a straight line, but we now know that because there must have been some distortion in making this map, that in reality that rhumb line isn't a perfect straight line across the surface of the Earth. So what actually is a perfect straight line across the surface of the Earth? Well, we call these lines great circles. In other words, a great circle route is anything that travels around the complete circumference of the Earth. So the obvious great circle is the equator. That's going to be a great circle. And in fact, if we wanted to fly from somewhere on the equator, somewhere in Africa here to somewhere in South America here, we could fly along here, the great circle, and we'd fly, exactly 0 degrees to get, along this 0 degrees line of latitude. So in other words, we could fly exactly west at 270 degrees, and we'd get to South America flying along here. And this is a great circle. Now, all lines of longitude are great circles because they are circles that run all the way around the Earth. But lines of latitude aren't great circles because they are just points that go around the Earth this way. So they're not great circles. But you can probably see that there are great circles. You could actually construct a great circle anywhere you liked in reality. So if I wanted to say fly from the UK here, and from London, and I wanted to fly from let's say to New York, I could draw a line on this globe that would go round here, and it would go all the way round the back of the Earth, all the way round and back to London. In other words, I could stretch a rubber band round the globe, and that would be a great circle. And if I wanted to fly from London to New York, I would want to fly that great circle route. And curiously, if you look at a globe and you fly from, say, you do that and you fly from London to New York, you'll notice that in fact, the great circle route takes you right through the top of Canada and takes you right down the coast of America. But of course, that's not, if you look at a Mercator projection, you don't think, because that's the quickest way of getting from London to New York. In other words, you're going from London to New York, you're going right through sort of Newfoundland and right through this eastern Canada, and you're flying more or less south down the coast of America, aren't you, to get to London. But of course, as we all know, when we've studied geography, we look at a chart and you tend to find that if you looked at London to New York, well, this is north, so you'd actually be flying sort of in this direction, wouldn't you? But obviously that direction isn't actually the great circle route. This is a classic difference between the rhumb line and the great circle. So the great circle route would be this route directing New York. And in fact, if you've got a map out of the Atlantic with New York over here and London over here, the Great Circle route would actually be a big curve like this. And it would go up from London, round as a curve, and all the way down to get to New York. So that would be the Great Circle route we'd have to fly, not the line we drew from London to New York, because that'd be a really dopey way of getting from London to New York, would be to take a map, to take a chart and just draw a line on it and try and fly that line. So in other words, any time we're navigating, we want to be able to navigate great circles, but we've got no way of drawing a great circle on a chart. We can only draw run lines on charts. Now, GPSs, when you ask a GPS to take you from A to B, the GPS will always calculate a great circle route. So in other words, if you don't see this in aviation very much, but certainly you do in yachts. If you're going on a big journey and you put that journey into GPS, and then from there you produce your plog, then you tend to find that the heading the GPS gives you isn't the same as the heading that you've drawn on your map, that you very accurately measured. And of course, the reason is that the GPS has calculated your great circle route, and the line you've drawn on your chart is a run line. And of course, a run line isn't a very, very good way of getting from A to B. And in fact, you could actually sail your run line. Yeah, you could point your boat on that run line course and you could actually sail it. But in reality, instead of going across the globe as a perfect great circle, what's happened is that you've actually gone a curve to get from A to B, which is a really silly way of doing it. So that's the difference between run lines and charts. Run lines and great circles. And this whole difference between run lines and great circles is obviously what makes navigation quite an interesting and quite a complicated subject, just purely because we can't get a globe and from a globe make it into a flat sheet of paper. And because it's flat sheets of paper is what we want to navigate by. So what's the difference between a chart and a map? Well, a chart is basically a projection of the Earth, as we've talked about. And a map has other things put into it. So, like for example, typical things that would be on a chart would be what's called the topographical features. Like for example, the mountains and things like that. And a map will have extra things that might be useful for the purposes of navigation and things like that. So in other words, it might have rivers and other things, valleys, lighthouses, churches, maybe even airports and beacons and things. So there is a difference between a map and a chart. So when we're talking about topographical charts, a topographical chart is like a normal chart, but it has different colours showing hills and terrain, and obviously the difference between the sea and the land. The seas are blue, the land is shown in like a typical brown colour. And for the purpose of navigation, when we're using a topographical Lambert's conformal chart, we need to be able to measure distances. So that means that all charts have got a scale. And what this scale is, this is showing you the difference between a distance measured on the chart and a distance in reality. And the scale is typically put as a ratio. So like, for example, a 1 to, let's say, 500,000 chart. This is what's called a half mil. Chart. That means that 1 inch on the chart represents 500,000 inches in reality. So, Claire, knowing that 1 inch represents 500,000 inches, how much would 1 centimetre represent? 1 centimetre measured on the chart, what would that measure in reality?
About 250,000.
Well, it'd measure 500,000 centimetres, wouldn't it? Yeah. So in other words, that it doesn't matter what the unit of measurement is. This could be converted directly to any measurement at all. So how do we know then when we pick up a chart, Claire? How are we going to find out what the scale is? Do you reckon?
It'll be written on there.
Yeah, there we go. Right in the bottom corner, it says that it's got the scale. This one's called a quarter mil chart because it's 1 to 250,000. It's showing the what the sheet number is, its edition, and all charts will show a little bit showing you where this chart is relative to other charts. So that's this piece here, and this is showing you the elevations. Now, I want you to read, Rob, what does that say there about magnetic variation?
Sorry, yeah, so magnetic variation for 2000 is approximately 3 minutes 30 seconds or 60 mils over the entire area. Annual rate of change is 2 minutes or half a mil increase. Full stop.
Well, what the crap does that mean? Can you explain it then, Rob?
So as you said at the beginning, the magnetic north moves all the time. But
Yeah.
what it's saying, the difference between mag and grid for this chart or map is 2000 for every 3 minutes and 30 seconds. So 3 minutes and 30 seconds is an angle, or 60 mils over the entire charts area. So you have to allow for the difference between the two when you plot your, did you call it a run line?
Okay, right. There's a few things there. Let's get a few facts down then here. Okay. Right. So what this is saying is that in the year 2000, the variation was 3 degrees 30 minutes. Yeah, and it changes at 2 minutes. It increases by 2 minutes every year. So that means in 2024. 24 years has elapsed since 2000. So that means it has increased by 24 times 2 minutes. So in other words, it's actually 48 minutes in more. So what is the magnetic variation today? In in March 2024 for this chart?
So would it be 27 minutes, 30 seconds?
No, it increases.
Oh, yeah.
So in other words, it's going to be 48 onto 30. In other words, that's going to be 4 degrees at 18 minutes. So if we were navigating this chart now, we would use the closest that would be to a degree is 4 degrees. So in other words, we would say that the magnetic variation in Cyprus at the moment, as of today, is about 4 degrees. Yeah. So that's the difference between true north and magnetic north for this chart. So the main thing about the scale is the fact that the scale is 1 to 250,000. In other words, this is called a quarter mil chart. And as Claire said, if we measured 1 inch, sorry, if we measured 1 centimeter on this chart, 1 centimeter would show how many, it would be 250,000. So in other words, 1 centimeter distance on the chart would be 250,000 centimeters. So how many centimeters in a meter? There's 100. So that means 1 centimeter would be equal to 2,500 meters. In other words, 1 centimeter equals 2.5 kilometers. How many nautical miles is that, and how many statute miles is that? I want to know how many miles that is and how many nautical miles. How are we going to calculate that? Okay, let's work. There are plenty of exam questions that will ask this, so let's work that one out, shall we? First off, let's take a guess at the answer. We've measured 1 centimeter on a quarter mil chart, and we know that that's 2.5 kilometers. So we've already worked that out, which we can do in our head. So take a guess, guys. How many miles is that going to be roughly? 2.5 kilometers. How many miles is that, Rob?
Probably 4.
1.5.
What if you're going down the motorway at 50 miles an hour, how many kilometers an hour is that roughly?
$80.
Yeah, it's about 80, isn't it? In other words, if we do 100 kilometers an hour in Cyprus on the motorway, that's about 70 miles an hour in the UK, isn't it? So a kilometer is slightly smaller than a mile. So that means that 2.5 kilometers, because we know that's smaller, that's going to be, let's take a guess, it's going to be about 1.5 miles, all right? At a guess. That's my guess. Now let's work it out a bit more accurately. So if you guys can grab your whiz wheels. So the question is, how many how many nautical miles is 2.5 kilometers? So what I'd like you to do is look round your whiz wheel now. Let me just get my whiz wheel. Right, can you see at the top of your whiz wheel, it's got all the way printed around the edge, it's got above the 10, it's got kilometers, meters and liters. Can you see that? And then look around the edge. Can you see it's also saying it's got another bit that says yards? Yeah. And keep looking round the edge. It's got another bit that says, whoops, imperial gallons. And then another bit that says feet. Another bit that says nautical miles. Another bit that says statute miles. And these are all showing you things of how we can convert one to another. So the way it works is you put the on your whiz wheel, put 2.5 underneath the bit where it says kilometers. So can you see there? I've put 2.5 underneath kilometers. Yep. And then move your whiz wheel round until you find the bit that says nautical miles, which is there, and then read off under the nautical miles what it is. So for that, what I'm going to do is I'm going to move my little cursor so it lines up with the line that says nautical miles, and then I can read off directly under my cursor what that is. And on my one, it says that it's 1.36 nautical miles. Is that roughly the same answer as you guys got?
Yeah.
So in other words, so our original, we had a guess of 1.5. And in fact, 1 centimeter is in fact 1 point, what did we say it was? 3.5, I think you said, didn't we? Did we say 1.35, I think?
Yeah, 1.35.
Yeah, 1.36, something like that. Nautical miles. So there's always an exam question that will say this is the chart scale. You measure something on the chart. How many nautical miles is it, or something like that. And because you can convert anything to anything, you can even like convert things like when it says you measure 1 inch on a 1/4 mil chart, how many nautical miles is it? Well, it's exactly the same way. You could if you've got an inch, you then know that with a calculator you could then multiply 1 by 250,000. That gives you 250,000 inches. You could divide that by say 36, and that will give you how many yards it is, because you've got your calculator, and then you could use your whiz wheel to convert yards to nautical miles. Or if you could remember the fact that there's 1,760 yards in a mile, you could then say, right, okay, and I could then divide that by 1,760, and then I could then convert that statute miles into nautical miles by once again aligning the two up on my whiz wheel. Or if you really wanted to, you know, if you knew that, for example, 1 inch was say let's say 2.54 centimeters, you could just multiply 2.54 by 250,000, divide that by 100 to convert it to meters, divide that by 1,000 to convert it to kilometers, and then you could then do a simple kilometers to nautical miles conversion on your whiz wheel. But there'll be exam questions on these conversions, and you can use your whiz wheel, or if you want to commit a few sort of simple things to memory, that's always handy, and then you don't actually need to use your whiz wheel. You can do it directly. So we've got to measure distances on charts. Now, we're talking about nautical miles, and we're talking about feet, inches, statute miles, kilometers, centimeters, meters. I mean, what the crap are they? Yeah, where do they come from, and what determines them? Well, inches and feet are all bits of Henry VIII's anatomy. So that's where the standard of inches came from. So, you know, a foot is how big Henry VIII's foot was. They measured it and they said, okay, that's a foot. And they said, well, there's roughly 12 toes, so we'll call that an inch. So we'll divide the foot into inches. And then we want to measure strides. So what we do is we take 3 of those feet, make roughly 1 pace. So that we'll call that a yard. And so this rather inexact system became a measurement of the some imperial measurements that we use. The French, of course, didn't want anything to do with the English monarchy, so they invented their own system based around meters, and they just got a piece of metal, and they just like said, okay, this is from now on in, this is a meter, and that became like the worldwide standard of what a meter was. And then you could take your things to it. You could very accurately measure that 1 meter and transpose that. And it was a physical a measurement that was placed in Paris. Times moved on, and that we don't actually measure anything in reality anymore in terms of physical, because we now know that anything that we measure will change over time. You know, molecules and molecular deposition and things will change anything. So everything nowadays is measured in terms of time, which we can measure to millionths of a decimal place if we need to. Plus the fact that time is completely analog, whereas all these other forms of measurement are not necessarily totally accurate, because you can get to the point where you're dealing with molecules and things, in which case you can't measure them totally accurately, because obviously molecules move and all sorts of things. Nautical miles is based on navigation. It's actually 1/60th of 1 minute of latitude. So where we when we just measured all these lines of latitude, if we take every line of latitude and we divide it into 60 parts, in other words 60 minutes, each of those minutes is 1 nautical mile. So if I wanted to say, well, if we wanted to get from the equator, if we're flying from somewhere here in Africa on the equator, and we wanted to fly to let's say, I don't know. I lost my chart. Where'd I put it? Lost my bloody thing, haven't I? Here we go. Right, suppose we wanted to fly to, say, London. That's 52 north. Roughly how many nautical miles would that be, roughly? We're going to fly directly north from the equator to London. And London is 52 degrees north. What do you reckon?
I'm not sure, to be honest with you.
Well, what is a nautical mile? What's the definition of a nautical mile?
What is it? There's 1 kilometre, 0.54 nautical mile.
No, what is the definition of a nautical mile? It's not a bit of Henry VIII's anatomy, and it's not a bit of a metal rod, a platinum iridium rod based in Paris. What actually is a nautical mile?
It's a unit of measuring the distance over sea.
Yeah, and what is it? How did it come by? How did it come by? How was it invented? What actually physically is it on the planet?
I don't know.
Help him out, Rob. What's a nautical mile?
I'm almost at a loss. I'm trying to remember something to do with knots on a rope behind, or is that speed? I'm totally
No,
lost.
that's speed. That's a bit of rope you throw out the back of a sailing boat. Nothing to do with
Look at how fast you're going. I don't know.
Right.
Claire?
So remember that there's 60 minutes in every degree of latitude, and a nautical mile is 1/60th of a degree. In other words, 1 nautical mile equals 1 minute of latitude. So that's what a nautical mile is. There's 60 of them in every single degree of latitude. So if we go from the equator to London, which is 52 degrees north, in other words, we've traversed 52 degrees of latitude, then the distance between the equator and London must be 0 to 52 degrees. In other words, is 52 degrees. 52 times 60 equals, what is 52 times 60 is going to be, say, 3,120. Yeah. So in other words, we know that the distance between the equator and London is going to be about 3,120 nautical miles. In other words, we're going to be 52 degrees times 60 is 3120. So if we look at a typical aviation chart, and we look on the right-hand side of a typical aviation chart, you'll see that the lines of latitude are actually marked on the chart. So if we look across the Humber Wash, for example, here, where are we here? I want to just get this in the right place. There we go. Can you see on the right-hand side of the chart the 53 degrees north line of latitude. There we go. And the 53 degrees line of latitude actually runs, there we go, straight through the Humber Wash. And the 52 degrees line of latitude generally goes straight through the top of North London. So there's the 52 degrees line of latitude, and you'll see that if I follow that all the way across, it goes straight through Stansted Airport and heads more or less across the top of London through Stevenage, Luton, and all that sort of gear. So how many nautical miles do you reckon it would be roughly from Stansted to the Wash? If I wanted to fly straight from Stansted Airport to the Wash, which is directly north, how many nautical miles is that, Claire? Roughly.
Could you explain that again, please?
Yeah, so the line of latitude, the Wash is on 53 degrees line of latitude. Stansted is on 52 degrees line of latitude, and Stansted is directly below the Wash. So if I want to get from
It's
Stansted
60.
to the Wash, yes, it's 60 nautical miles, because we're traversing 1 degree of latitude, and we know that 1 degree of latitude is 60 nautical miles. So it's about 60 nautical miles from Stansted to the Wash. But it's only because one of them is directly north and south of another, and we can do this trick. Now, the other method of measuring distance on a chart is a bit easier, because you could probably see that to measure any distance on a chart, what we could do is if I want to know the distance between anywhere, I could get a pair of dividers, I could put it on the chart, and I could take it to the latitude, and I could count how many minutes it is, and that would tell me the distance, wouldn't it, in nautical miles? So that would be a very good way of measuring the distance, wouldn't it, between any 2 points? So I could just, if I wanted to measure the distance between what here and here, I could just measure that with a pair of dividers, and I could then put it on this scale on the chart here on the right hand side, where it's all where you've got all these graduations, and I could measure it up there, and I could see how many minutes of latitude it was, and I could work out how many nautical miles it was. Why do you think, Rob, why do you think if I wanted to measure a distance, I just said I could take my dividers and I could put them on this line here? I mean, surely if I wanted to measure the distance between, say, here and here, and I took my dividers here, why can't I just put them, say, here and measure that distance there?
Because the further north you go, the further the scale increases.
Yes, so
going back to that projection
exactly
of the
right.
map.
So in other words, if I want to measure the distance here, I then need to use, ideally, this distance here is going to be more accurate, isn't it, than measuring it down the bottom. Well, if I want a question for yourself, if I wanted to once again measure the distance from here to here, I mean, with a pair of dividers, I've said that I could move them round to here and measure how many minutes it is in lines of latitude, and that would be nautical miles. But I mean, that's a bit of a pain in the ass. I mean, why can't I just measure it across here? Look, there we go. Look, I can measure the minutes across there, can't I? In other words, I could measure the minutes of longitude. So why can't I measure the minutes of longitude? Why am I measuring minutes of latitude?
Yeah. Well,
You've got to get your head around this one and think about the Earth and longitude and latitude. And
what was the question? Sorry.
the question is, if I want to measure a distance on a chart, why am I measuring it in minutes of latitude? Why can't I measure it in minutes of longitude?
When you're traveling east to west.
No, the reason is, think about the logic and what's going on here, is that lines of latitude extend around the Earth this way, and we're measuring how much they change as we go north or south. So that means that 1 degree of latitude here is the same distance as 1 degree of latitude here. But longitude, if you remember, is the lines, we've got them going around the Earth this way, haven't we? So that means that if we measure the distance between here and here, and the distance between here and here, even though they're covered the same degrees, the distance is totally different, isn't it? Because if you imagine a degree of longitude here is going to be quite a large amount, isn't it? But a degree of longitude near the North Pole is going to be nothing, is it?
Yeah.
So you can't measure any distance measuring horizontally on a map, because it doesn't make sense, does it? Because you can only measure the distance of the vertical scale of the lines of latitude. So we can measure distance 2 ways so far. We can use the scale, and we can mathematically work it out. In other words, we could measure it in centimeters and then use some sort of mathematics to convert that to nautical miles. We could measure it on the edge of the chart. There's another way we can measure distance, and that is if we look at the bottom of the chart, where it has the scale. Right, can you see where it says scale 1 to 500,000? Yep. But can you see next to that, there's like a ruler, isn't there? And this ruler is calibrated, and you can actually measure off. You see, it says statute miles, nautical miles, and kilometers. So that you could actually just measure statute miles, nautical miles, and kilometers just on the bottom of the chart, couldn't you? You could actually just like go to this scale here, and you could see that you could start at naught and just like put it on here and measure it directly at the bottom. And there is a 4th way of measuring distance, which is what everyone does in aviation. And because we know that maps, aviation maps, are always made to be 1/4 mil or 1/2 mil, you can actually just cheat, and you can buy a ruler. And this is a typical ruler, and you'll notice that if I just show you this typical ruler, can you see it actually says on it, you've got one side of the ruler says 1/2 mil, the other side of the ruler says 1/4 mil, And in fact, this ruler is actually made to be a 1/4 mil or 1/2 mil, and it's actually already measuring nautical miles. And then there's an inner scale that's automatically measuring kilometers and statute miles for you. So if I wanted to, if I was using, say, a 1/4 mil chart, what I would do is I would use the scale that says 1/4 mil, which is that one, you see. And then that means that I could then use this scale across the top here that's reading nautical miles directly. So having said all of that, if I want to know the distance between, say, Akrotiri and Paphos Airport, what I could do is I know that I know I've got Akrotiri here, and then I've got Paphos Airport up here. So I know that this chart is a 1/4 mil chart. So what I could do is I could find my ruler at 1/4 mil, and then all I've got to do is to measure the distance between Akrotiri here and Paphos here using the 1/4 mil part of my ruler, and it says it's 30. No, it says it's 27 nautical miles. So what you need to do is you need to get, as part of your flight kit, you need to get one of these scale rulers. Now you can also get them as a you can buy little protractors like this as well. So what this is a combination where it's giving you a protractor like this, and it's also, if you notice, it's got two scales on it. One that says which is also giving you the conversions. Or you can just buy a simple protractor to measure angles with. I mean, I generally don't use these. I find that I use an old-fashioned protractor and an old-fashioned ruler. But then, you know, I'm very much a sort of marine guy, so I'm used to like dealing with protractors and rulers. But a lot of people prefer, you know, some of these more modern sort of aids like this that have got it all in one. So that's how we convert feet to meters, kilometers, things, chart scales, and how we use the ruler. So what I want to do now is I want to actually run through a bit more detail on a chart, the sort of things that we're going to find on a chart. So I'm going to use the UK chart, and I want to just run you through some bits and pieces on a UK chart. So you can all see a right. So you can all see the UK chart. Right, let me just make that big. Right, here we go. So at the bottom corner here is where we've got the scale. One to 500,000. We've also got the this ruler we talked about. Now we've also got all these legends. In other words, all the different things that's on the chart is giving you a bit of an idea about what some of the things are. We're going to discuss those in a lot more detail. We've got other little legends on the chart here showing various frequencies, danger areas, and all sorts of things. Now, let's look a bit more at the lines of longitude and latitude. So you see here, we've got this one here that says 52 degrees north that we were talking about. So we know that 52 degrees north goes roughly through Stansted. And then let's just scroll up 52, and then we get to 53 degrees north here. So let's just get the two on the same screen. So there we go. We go 52 degrees north, 53 degrees north. So these are lines of latitude. And you'll notice that they're curving on the chart. So that's not because I've scanned it on the PIS. In fact, this is a very, very accurate precision scan. It's not actually a photograph. It's I put this through my scanner, a very big professional scanner, and you'll see that it is. Oh, for God's sake! I don't want to epoxy what's going on here. Rah. Now it's zoom me out. Yeah, you'll notice that the lines of longitude, as we've discussed earlier, they actually do bend a tiny weeny bit. So there's 51 and there's 52. So then this line across the middle here between them, this is obviously going to be 30 because we know that the 60 minutes go from 51 to 52. So whatever goes from here to here, there's going to be 60 of them. So this is 30. So that means that these big dashes here are going to be 10 minutes. Those we got 10, 20, 30, which is the middle, 40, 50, 60, which is going to be 52 degrees north. So from 51 degrees north, we know that that's 10 nautical miles away. So that means that each of these little ticks here is 1 nautical mile. So this is 51. That means this is 51 degrees 10 minutes north. So the Lundy Islands here is going to be 51 degrees 10 minutes north. Yeah. Now, what about Lundy Islands east and west? Right. Well, we know that this is 4 degrees west. So this is 5 degrees west. So that means that this is going to be 51 degrees 30 minutes west. So that 51 degrees 30. So that means that this is 10, 20, 30, 40. So we know that the Lundy Islands are going to be roughly 51 degrees and 40 minutes. What am I talking about? Sorry, Paul. Sorry, your instructor is talking a lot of bollocks here, isn't he? I'm not. I should be looking at my screen here, shouldn't I? Right. So, right. Start again. Of course, it's not. That's somewhere in the Atlantic. Is somewhere. Right. So this is 4 degrees west. This line here. This line of longitude. This is 5 degrees west. line of longitude. So this is 4 degrees and 30 minutes west. So that means that Lundy Island is going to be roughly 4 degrees, 10, 20, 30, roughly 4 degrees, 40 minutes west, and roughly 51 degrees, 10 minutes north. Yep, so it roughly intersects there and there. And if we wanted to measure the distance between, say, this helicopter port here, this H, which is helicopter from Bideford to Lundy, what we could do is we could measure that distance there with a ruler, with a scale ruler, or we could actually just measure it with a pair of dividers, and we could put it up here and measure it here. And we can see that between Bideford helicopter port and Lundy Island, I reckon is going to be about, I can see it's going to be about 21 nautical miles, isn't it? It's going to be about from there to there, measuring that latitude. So that's how we can then use all of these latitudes and longitudes to actually work out to specify any one point in latitude and longitude. So what else is there useful features on this map? Let me just go into this corner. Right, so it's showing you that it's got motorways, dual carriageways, various other things marked. But the main thing I want to talk about is this one here, is the line contour lines. Now, a contour line is a line showing equal height above sea level, and each of them are coloured differently. So as we get higher, they go darker brown. So this is how you can tell where all your hills are. So the darker it is, the more hilly, the more higher the hill is. So you can see at a glance that most of Wales here is going to be quite hilly, isn't it? Because it's a lot of dark brown in it. Whereas if we go to, say, the East Anglia, there's not very many hills at all here in East Anglia. In fact, there isn't. I don't think there is a hill in East Anglia. So so we've got the contour lines are showing us lines of equal height, and in fact you can actually see the contour lines. All right, if I zoom right in to a chart, let's go to Wales, which we know is all pretty hilly to start with, shall we? There we go. And you can actually see the heights above sea level are actually marked on the chart. And you see you've got these contour lines here. So you've got 1,000. So this is showing you 1,000 feet above sea level. So everywhere on this line here is 1,000 foot above sea level. And you'll see that you've got these dots. Well, these little dots are spot heights. So that little black dot is 1,444 feet above sea level, which is kind of expected, really, because if that's the 1,000 foot contour, then that must be slightly higher than 1,000 foot, and that point here must be slightly lower than 1,000 foot. And some of them go quite high. You can see that you've got a 1,500 foot, 2,000 foot, nearly 3,000 feet here. And these are all showing you the heights on a chart.